So now we can draw the molecular orbital picture of the carbon monoxide molecule based on the hybridization concept. Right, so let us place the hybridized orbitals. So towards the left we will be drawing carbon atomic orbitals, and towards the right we will draw the oxygen atomic orbitals. Right, okay, so carbon should be placed higher as it is less electronegative, so that rule we have to follow. Okay, so this is how we have placed it up above. Let's create some space. Okay, and then the oxygens. So what are these orbitals? So carbons hybridized to spz near the 2s orbital, low energy 2spz that we discussed just now, and the high energy 2spz which is near to the pure 2p orbital. 2p will have only two orbitals because one of the orbitals, that is the pz, has been involved in the hybridization. So this is how we place the orbitals. Okay, now for oxygen. Okay, so oxygen atomic orbitals should be located towards the lower side energetically. So the oxygens to spz will be quite low, like this, to spz. The low energy to spz similarly for oxygen, and the high energy to spz. This high energy to spz is near to the low energy to spz of carbon. As you can see, this low energy to spz of carbon is near to the high energy to spz of oxygen, right? So just be careful and please keep this in mind while drawing the diagram, that energy difference, where to place the atomic orbitals, that is very, very important. And now the p orbitals of oxygen are placed near to the, although lower than to spz of carbon, so it's very, very low energetically. So okay, so 2p of oxygen, pure 2p, only having two orbitals, because here also one of the pz is involved in the hybridization. Okay, now this is how we have placed. Now you can draw the molecular orbitals. Now if you just have a close look, these two orbitals, the 2spz lower energy and the 2spz higher energy, lower energy of carbon and higher energy of oxygen are close together. So that is why these two orbitals, they will give rise to the sigma bonding orbitals and antibonding orbitals, because they are near to each other energetically. So this is how we get the sigma and sigma star molecular orbitals. So okay, sigma and sigma star. So what you generally draw as sigma 2s2 and sigma star 2s2, so these are the orbitals, right? And what happens to this low energy 2spz oxygen atomic orbitals? See, this is energetically quite far to these two orbitals of carbon, right? This is far and this is also far. So low energy and high energy of carbon is very far from the low energy to spz of oxygen. So that is why there it cannot form a molecular orbital, and because their energies are unaffected by each other. That is why now this orbital will form, to spz low energy of oxygen will form an orbital which is known as the sigma non-bonding orbital. So this is how the non-bonding orbital will come into existence, and we'll draw like this. Because it is unaffected, it cannot form a molecular orbital. It forms its own molecular orbital which is non-bonding, right? Like this. Okay, so we have seen sigma non-bonding, sigma bonding, and sigma star anti-bonding. Now coming on to the pz, coming on towards the p orbital. Okay, before that, one more non-bonding orbital will be seen. So this low energy of carbon and the high energy of oxygen, they have formed the bonding and anti-bonding orbitals, molecular orbitals. Now what is left is this high energy of carbon is again left. Now this high energy of carbon is again far from any of the pz orbitals, spz orbitals of oxygen. Now that is why, since this is energetically far away from any of this 2 spz orbitals of oxygen, now it will again form its own orbital, that is the non-bonding molecular orbital, NB. So hope you are understanding that why these non-bonding orbitals are getting formed, because they are energetically very far from each other. They are unaffected by each other's energy. That is why they form their own molecular orbital, right? That is the non-bonding molecular orbital. Now coming towards the P, I'll draw in different colors so that it is easy to understand. So P will, obviously they will give rise to the pi orbital like this. Okay, so this is next to the sigma, so 2 pi molecular orbitals. So what you call the pi px and py. So this is 2px and 2py pure. This is also 2px and 2py pure. So they will give rise to pi orbitals, right? Pi bonding orbitals, and also the pi anti-bonding orbitals like this. Pi star and pi star, right? Now we will name them in a different manner. Different means since we previously we had seen this 1s, sigma 1s, sigma 2s, and then pi 2px, then sigma 2pz. These were the nomenclatures previously. Now they will be simply named as 1, 2, 3, 4, whatever according to the sequence of energy, right? Sequence of their appearance. So this sigma, so starting with here, from here, so this one is sigma 1 non-bonding, then comes sigma 2 which is bonding, then comes pi 1 and pi 2 which is again bonding, right? Then sigma non-bonding comes this 3, sigma 3 non-bonding, then pi 1 pi 2, after pi 1 pi 2 it is pi 3 and pi 4, pi star 3, pi star 4, and lastly sigma 3 till sigma 3. So this will be named as sigma 4 anti-bonding. So like this we name in the sequence of their appearance energetically. So this is how is the picture, molecular orbital picture of the carbon monoxide molecule. So hope you are not getting confused, and hope this is easy to understand and all the explanations are clear. Now what remains? Only the filling of electrons. So now we will fill the electrons in the respective atomic orbitals and the molecular orbitals. Okay, now starting with the atomic orbitals. Since we have hybridized orbitals, so first let us see how to fill them. Okay, now first of all, the lowermost oxygen. So this is will go by order of energy. So let's start with the lowermost atomic orbital, that is the 2spz hybridized orbital of oxygen, the lowermost one. So since it is independent, so it will contain 2 electrons, right? And it will again generate these 2 electrons in its non-bonding molecular orbital. Okay, now coming to the 2spz high energy hybridized orbital of oxygen and the 2spz low energy hybridized orbital of carbon. So these two, okay, 2spz of carbon and 2spz of oxygen. So these give rise to sigma 2 bonding and sigma star. Since the molecular orbital contain 2 electrons each, okay, so 2 electrons each means each of these hybridized atomic orbital should contain one single electron, right? Then only they will give two electrons in their molecular orbital. So it might seem complicated, but this is not as complicated. So this contains one, this contains one, hybridized. Okay, that is why we have two in the molecular orbital. So sigma 2 bonding molecular orbital containing two. Now then moving on towards the high energy hybridized 2sp(z) of carbon. Again it is independent since it produces non-bonding orbitals, so it will contain as usual 2, and it will give rise to the 2 electrons in its non-bonding molecular orbital. Okay, done. Now coming on to the 2p atomic orbital of carbon and oxygen. What will happen to the 2p atomic orbital? Okay, so now 2p we know each will contain each will have the pi 1 and pi 2 bonding orbitals filled with 2 electrons in each. Okay, so we will have 2 electrons in the pi 1 bonding and pi 2 bonding molecular orbitals. So we have to get total 4 electrons like this. Okay, so how to accommodate these 4 electrons? So oxygen we know that it contains how many? So the 2p, since pz is involved in the hybridization, so 2p of this carbon should contain 3 electrons, right? The fourth one is gone for the hybridization. pz is gone, so 2p of this oxygen should contain 3 electrons. So we will write it 3 here, right? So 3. Hope you are getting I hope you understand this. So we are having 3. 1 is gone for pz is gone for hybridization, right? So pz is gone for hybridization. So 3 electrons. Now total we have to get 4, since we have filled 4 in the molecular orbital. So 1 is left. So this one will get into the carbon's 2py atomic orbital like this. Why I have not filled in the carbon's 2px atomic orbital? Because in the 2px of oxygen we already have 2 electrons, as you can see. So that is why only one we can accommodate here in the 2py of carbon. So that is why we have not added this single oxygen, single electron of the carbon atom onto the 2px. We have added it in the 2py because 2px of oxygen already contains 2 electrons. So this is the reason. So 4 we have. So 4 we have filled here. Now anything else is there? I don't think so, because the carbon and oxygen, so valence electrons we had counted how many for so carbon we had counted valence electrons as 4 and oxygen's valence electron as 6, so total 10. So accordingly we can write the molecular orbital configuration, right? So hope you are getting it. So we have filled the atomic orbitals based on the hybridization as well as the pure atomic orbitals. So molecular orbitals we will write kk. Okay, after that we will write kk, then sigma 1 non-bonding comes energetically, then sigma 2 bonding comes. After that what is there? Then there is pi 1 and pi 2 which is bonding, and then after that there is sigma 3 which is non-bonding. Okay, up to this only we will have to fill. Okay, now just fill 2 electrons in each. Sigma 1 non-bonding 2, this one is also 2 to 4 to 6 to 8 and to 10. So we have 10 electrons. Now easily we can calculate the bond order for carbon monoxide molecules. So number of electrons in the bonding molecular orbital and anti-bonding, that only we require. We do not count the electrons in the non-bonding orbitals because they do not involve in bonding, so they do not contribute in the calculation of bond order. So we will not count the non-bonding electrons. Okay, so we have how many? So we have only bonding electrons in the electronic configuration for carbon monoxide. So bonding electrons, no anti-bonding electrons we have, so only bonding. So as you can see there are 2 2 4 and 2 6. 6 bonding electrons minus 0 anti-bonding electrons divided by 2 is equal to 3. So bond order is 3. That means carbon and oxygen has triple bond in case of carbon monoxide molecule. And also looking at the molecular orbital electronic configuration, this molecule is diamagnetic, right? Why? Because none of the electrons are unpaired. All electrons are paired. That is why the molecule is diamagnetic. And also you can find some reference in several books that this is isoelectronic. Carbon monoxide is isoelectronic with nitrogen molecule, because nitrogen also contains 10 electrons in the molecular orbitals. Hope you understood that how we are filling the electrons in the atomic as well as molecular orbitals in case of carbon monoxide, and the bond order calculation also. So hope this is clear about the heteronuclear molecule, that is carbon monoxide, and hope it helps. Thank you.